is that what I was looking for, right, is negative um, 1/2. I guess I should have. I think it's because I don't think I wrote out the problem very well. I don't think it was a well written problem, if I'm going to be honest with you guys. Right? Because this rate law right here, right? So I think this is what I should have referenced it to, right? Is that you have the change in concentration of NO2, right, of delta T. That's going to be equal to K2 times the concentration of NO3 times the concentration of NO, right? And so then for the concentration of NO3, right, that's going to be then equal to, um, right, the change in concentration of NO3 delta T, right, is going to be equal to the forward and reverse reactions, right, of that equilibrium that we have up here, right? So what we can do then is we can take K2, right, and so then what we can plug in for the NO3 is the reaction of K1 over K minus 1 times the concentration of NO times the concentration of O2, right? And that's going to be times the concentration of NO in that scenario, right? Which is how I got those parts right there. And so that gives you then negative 1/2. This is just a poorly worded problem in retrospect now. Um, so I apologize. Hopefully, anything that's on the exam is going to be more properly worded in terms of what it is that I'm actually looking for. Right, so you have that right there, right? So that's going to then be equal to K2. And so you can either, right, so K1 over K minus 1, or so lowercase K1 over lowercase K minus 1 is equal to the equilibrium constant, right? Because, you know, in terms of a dynamic equilibrium, right, the rates of the forward and the reverse reactions are always going to be equal to each other. And those rates of reactions are always dependent upon the concentrations. And so, right, one reaction happening in this direction, right, should be equal to the reaction happening in the opposite direction. And that's why, you can just simply rewrite K1 over K minus 1 as the equilibrium constant for that reaction, right, which is what I'm going to do right here, K1, and that gives you that. And then you have NO2, 2, O2, right? And so now, probably one of the things that I think people were, most, that shouldn't be a negative, that's a positive value. Um, Probably then confused by, right, is where the 2 comes from. And so the 2 comes from, right, because essentially when you're writing out the rate, you're always writing out the rate for essentially just 1 mole of NO2 being formed. And so you have your whole rate system over there, but that's all in reference to, only doing like half the rate, so to say. And so you multiply that over. And so what you get is that the rate of the reaction, which is delta NO, change in concentration of NO2 over time, change in time, is going to be equal to 2K2 K1 NO squared O2, right? And so that's without using the steady state approximation, right? Which makes sense because the only time you really use the steady state approximation is if you don't know which reaction step is the fast step or the slow step. And that's how you come up with the mechanisms, because certain things start to cancel out in those scenarios, right? If they don't matter, right? And so I think that's kind of where I was running into the problem earlier when I was doing the applying the steady state approximations, that I wasn't canceling things out that needed to be canceled out in those scenarios. Um, but yeah, so this is the correct way to approach this problem, and I should have written it as determine the rate law in terms of the change in concentration or the production of NO2, but in reference to the starting materials.